So in today's lecture, we are going to discuss the Ampere circuital law, right? Ampere's circuital law. Ampere circuital law. What is the Ampere circuital law? Right. For example, if you consider this is the loop, right? This is the closed Amperian loop, right? And if you consider the many currents are passing through these loop like this, right? Suppose this is the I1, this is the I2, this is the I3, and this is the I4, right? Suppose this is the loop 1, right? And its orientation you can assume to be right like this. The orientation is the upward direction, and you consider the loop 2, right? This is the loop 2, like this, right? This is the loop 2, this is the current I2, this is the current I3, this is the current I4. Is it clear or not, you tell? And you may consider this the loop 2, and this is the orientation. Is it clear? Right. So now according to Ampere's law, right, you consider this is a closed loop and some currents are passing through these loops, right? So, and suppose you consider this is the loop and the magnetic field is produced around the loop, all right? When current carrying wire is there, suppose this is the infinite wire, right, or the finite wire. If the current carrying wires are there, around it magnetic field is produced. And if you consider an imaginary loop and the orientation is like this, so according to Ampere's law, if the magnetic field is produced, right, suppose it is B, right, vector B, and this is the elemental portion dl. So according to Ampere's law, the line integral of magnetic induction B, magnetic induction, what is the magnetic induction? Say B, right, along the closed loop, right, is equal to line integral of B dot dl is equal to mu naught, right, is equal to this is mu times is equal to mu naught times current enclosed in it, right? Current enclosed, I enclosed, right? What is this? This is the line integral. This is the line integral of B along the path or along the closed loop L, right? It represent, this circle represent, we are finding the integration for a closed loop, right? This is the line integral, and for a loop, right, any closed loop or any closed path, right, closed loop, it may be the closed path, any closed path or any closed loop. This is called the Ampere circuital law, right? In this case, the current where the I enclosed is nothing but I enclosed, which is taken with sign, either it is positive or negative, right, according to the orientation of the loop, Is it clear or not? For example, if you consider the loop 1, right, this is the loop 1 and its orientation is suppose given, right, and its orientation is upward direction. So this direction is taken to be positive and this direction to the negative, right, it is negative, or according to the orientation of the loop, right, according to with the help of right hand rule, right hand thumb rule. Right hand thumb rule. So according in the direction of the right hand thumb, right, it is the orientation of the loop, and right hand the thumb, it is taken with the positive side, right? If for this loop, right, if you want to write the B dot dl is equal to mu naught times I enclosed, right? So first of all, the current I1, I2 and I3 are enclosed current in it, not I4. Is it clear or not, you tell? So it is the positive direction. It is the positive direction. So I1 and I3 are taken with positive direction, while I2 is downward direction, right? So I1 minus I2 plus I3. This is the line integral of B dot dl for loop 1. Is it clear or not, you tell? While for loop 2, for loop 2, right? Mu naught times I enclosed, mu naught times. This is the loop 2. Suppose this is the loop 2. And loop 2 orientation is like this. So it means that it is downward direction. According to right hand rule, it is positive and therefore it is negative. Is it clear or not, you tell? The current according to the loop, right, orientation, this direction is positive. So you consider this is I2. So it is taken with positive. This is I3. It is taken with negative. And this is I4, also taken with negative. Is it clear or not, you tell? So what the terms will come over here? The I2 and minus I3 and minus I4. Is it clear or not? Copy this. Now let's see few illustrations. For example, suppose this is the loop, right? And this is the another loop. This is the current, right? Suppose this is the current 5 ampere. This is the 2 ampere, right? This is the 3 ampere, right? And this is the 1.5 ampere, right? If this is the orientation for the loop 1 and this is the orientation for loop 2, right? Find what? Find the line integral of B dot dl for loop 1 and loop 2. This is the question, right? Copy this. So let's see the solution, right? The line integral of B dot dl, right, for loop 1, right, is equal to mu naught times I enclosed. Mu naught, it is the permittivity of free space. If you consider, right, this is the orientation downward, right, like this. So this direction is what is taken as positive sign. Is it clear or not? Right. If it is positive, so it is positive, right? It is negative and it is also negative for this loop. Are you getting or not? You can consider, right? This is the orientation. If you consider, right? So this direction is what? Say positive, and therefore this direction is negative. All right. So it is along the orientation, opposite. So it is this is plus 2 ampere, right? It is minus 5 minus 3. So how much it is? Minus 6 mu naught. Fine. And what about the loop 2? B dot dl for loop 2, mu naught into I enclosed is equal to mu naught times. This is the positive orientation. I think you understand like this, right? This is the positive, right? This is the positive, and therefore this is negative. So if you consider this is positive, so this is positive and this is also positive. So it is 5 ampere, it is 3 ampere, and it is minus, it is negative, it is positive, it is positive, right? So it is equal to 3 plus 5 minus 1.5. So 6.5 mu naught, right, is the correct answer. Copy this. So let's see some other examples. For example, if consider these are the side views of the wire. Suppose this is the 2 ampere going into the board. This is the 1 ampere coming out. Cross mean into the board, dot mean out of the board. This is the 5 ampere, right? This is 1.5 ampere, fine. And this is 2.5 ampere. Now if you consider this is the one loop and this is the another loop, right? This is the 1 ampere, this is the one loop. So this is the loop 1 and this is loop 2, all right, loop 2. So its orientation is like this, its orientation is like this. You have to find the B dot dl, integration, line integral of B, right, for loop 1 and loop 2, for loop 1 and loop 2, right? This is the question. Copy this. So for the loop 1, right, this is the loop 1, right? What is the orientation of the loop 1? Say anti-clockwise sense, right? If this you consider this the loop 1, so what are the current enclosed by it? This is the 2.5 ampere, right? Yes. And this is 0.1 amp, this is the 1 ampere, this is cross 1.5 ampere. This is the orientation, I think you understand. So the up direction out of the board direction is taken with positive. So it is positive, mean it is positive, it is positive, therefore into is the negative. So B dot dl, for loop 1, the name of the loop 1 is written here, right, is equal to mu naught into I enclosed. It is taken with 2.5 plus 1 minus 1.5. It is equal to what? 3.5 minus 1.5 is equal to 2 mu naught, right? Yes. It is value of B dot dl for the loop 1. Fine. Yes. For the loop 2, for loop 2, this is the loop 2, right? This is the orientation, right? This is the 1 ampere, this is 2 ampere, this is 5 ampere, right? It is the clockwise sense, so into the direction is taken with positive sign, right? These two currents are not enclosed, first of all, and second thing, into the board is positive, positive, negative, negative, right? It is loop 2. So what is the B dot dl util? Is equal to mu naught times I enclosed. The I enclosed value is 2 minus 5 minus 1. This is minus 4 mu naught, right? B dot dl loop 2. All right. Copy this. For example, we have the loop like this, right? This is the loop, and the current is like this. Is it clear or not? And this is the current and this is the current. This is the 2 ampere, this is the 3 ampere, right? So you have, this is the orientation of the loop. Find B dot dl, right? So to find the B dot dl, what you have to consider, listen one thing. If this is the loop, right, you may consider this is the loop, all right. So if you consider this the orientation, fine. So if this the orientation is downward, is out of the board, and it is into the board. So this current is taken with, tell me, mu naught I enclosed -2, and this is into the board orientation for this part, right? It is positive, but this current is what? Out. It is also negative, -5 E naught. All right. So this is the value. Copy this. Copy this. For example, there are so many loops like this. This is the loop, right? This is 2 ampere, 1.5 ampere, this is 3 ampere, and this is, right, 1 point, and this is 3.5 ampere, right? This is the orientation of the loop. All right, like this, like this. So you have to find the value of integration of B dot dl for this loop, right? Copy this. So how to solve this? Integration of B dot dl for this given loop, right? Suppose this is the loop. This is what? Out of the board orientation, please tell. Yes. So this is, tell me, minus. So this direction is positive, but the current is into, right? So the current enclosed, this current will taken as the minus sign. This is the into the board, but this current is out. So again it is taken with, right? This, the orientation of the loop is what? Like this, like this. So this is the out is the positive. So in is negative. And this is what? This is the clockwise, right? So it is the direction which taken with positive sign. So it is into the board, which is matching with the direction of orientation, right? So it is plus 3.5. So mu naught, it is how much? 5 minus 6.5 plus 3.5 minus mu naught 3.5. 3.5 mu naught is the B dot dl for loop, given loop. Is it clear or not? Copy this. Now see, let's see the application of the Ampere's law, right? Application of Ampere's law. Applications of Ampere's law, right? First application, you have to find the magnetic field due to infinite current carrying wire. Current carrying, right, wire. Infinite current carrying wire, right? Suppose this is the wire having the current I and it is going up to infinity. Is it clear or not? You tell. And at distance r we have to find the magnetic field. So to find the magnetic field, as we have done in case of Gauss's law, right, we have to choose the Amperian loop. Here the Amperian loop I am taking, this is the circle, all right, and at point P we have to find, is it clear or not, you tell? And this is the current I, right? Due to symmetric wire, if you consider the small portion over here, right, this is the current I, right? This is the current I, like this, and it is the orientation. So if you consider the small elemental wire and the magnetic field is B, so the B and dl both are in the same direction. So to find the magnetic field around this closed loop, right, you will apply the Ampere's law. Ampere's law is what? Mu naught into I enclosed. So what is the current enclosed in this wire, in this loop? This is the Amperian loop. Amperian's loop, which is the circle of the radius r, and the current enclosed here, it is I. Fine. If you consider what is the angle between B and dl, this, if you see the top view, right, this is the Amperian loop and the current I is coming out of the pole, and if this is the dl vector, this is the b vector. So everywhere, every time, the b is and dl are in the same direction. So what is the angle between them? Is 0. So b dl cos 0, right, is equal to mu naught I. And when you are integrating the b is constant everywhere due to symmetry. The b is constant every time. So it comes out of the integral and integration of dl. So if this is the dl portion, the radius is r. So what is the integration of this? Say 2 pi r. B into 2 pi r is equal to mu naught into I enclosed, right? B is equal to mu naught I. Suppose this is the I, right, upon 2 pi r. So this is the magnetic field as a function of r. Is it clear or not? So magnetic field is inversely proportional to r, right? If you draw the graph, due to the magnetic field, due to the current carrying wire between magnetic field and distance, a distance r, b and r, the graph is hyperbola, because at r is equal to 0, if you put r is equal to 0, the magnetic field at r is equal to 0, 1 upon 0 tending to infinity, and r tending to infinity, when you put the infinity over here, and 1 upon infinity become 0. So b varies hyperbolically here, right? Copy this. So the next application is b due to, right, b due to hollow cylindrical, right, current carrying conductor, all right, hollow cylindrical current carrying conductor. Suppose this is the cylinder, all right, if this is the cylinder, hollow, infinite, it is infinite, and the current carrying cylinder it is. Are you getting or not? Like this, right? The current is carrying, because it is hollow, outside is air, inside is air, here is also air, but this is the material you can consider, right? This is the material you can consider. Are you getting or not? So the current is carrying along the curved surface or the lateral surface, you can say. This is the current. Are you getting? And the current is I. All right. Yes. Like this. Now you have to find the magnetic field. Listen one thing. You have to also make graph between the magnetic field and the distance from r is equal to 0 to r. This is the inside, right? The current is going on along the circumference only, and this is the distance r, right? So there will be the two cases, right? First case is what? There will be two cases. The first case, case 1, the inside mean this is the axis of the cylinder. The point P lies here at distance small r. The radius of the cylinder is capital R, you can think, all right? And the inside point mean this point is greater than 0 and less than r, right? Inside mean, all right? To find the magnetic field at this point, what will you do? You will consider the small Amperian loop, all right? And suppose this is the orientation of the Amperian loop, and you will apply the Ampere's law. Apply the Ampere's law, right? What is the Ampere's law? You tell. Integration of B dot dl is equal to what? Mu naught times current enclosed. Are you getting or not? Yes. What is the current enclosed in this loop? No, what is current enclosed in this loop is 0. How it is 0? Look, if you see from the top view, this is the cylinder, right? And the current is distributed over this circumference, like current is coming. Here it is air, this side is air, right? So in the material current can come out. So this is the total current I, right? This is the total current I is distributed along the circumference, along the lateral surface. I have chosen this point at distance r. So if you are assuming this is the Amperian loop, if this is the Amperian loop, if you consider this the Amperian loop, right? Or the orientation is like this, the Amperian loop, right? So what is the current in this Amperian loop? Tell me. 0. So the current enclosed here is 0. And if you take B common, integration of dl, right, it is 0. Although this is the elemental distance dl, right? Dl vector. So if you, this is the dl vector element. So if you integrate this, integration of dl will be equal to 2 pi r. So here its value will be equal to 2 pi r, but b will be 0. That is from 0 to capital R inside, from axis to on the surface, every point inside the cylinder, the magnetic field is what? Say 0, right? Copy this first. So now consider the case 2. What is the case 2? Say outside. What is the meaning of outside? Mean the point P is outside. From R is equal to capital R less than infinity, right? It means you consider this the point P, and at distance R from the axis, this is the axis of cylinder, and now you will consider an Amperian loop like this, right? The orientation you can take like this. If you take this orientation along the direction of the current, right, and you choose the elemental portion of dl at this point, magnetic field is B, right? If you look here, this is the point P outside, right, and this is the Amperian loop, and you are taking what? You are taking the small elemental portion dl, and this is the B. So if you consider what is the theta, the theta over here is 0. Now along this Amperian loop, apply the Gauss's, apply the Ampere's law, mu naught into I enclosed. Yes, tell me, in this Amperian loop, right, in this Amperian, what is the current enclosed? All the current I, right, it is I, and it is B dot dl, right? Dl, integration of dl is what? This is the elemental portion. If you add them, what will you get? The circumference, say 2 pi r mu naught I. So B is equal to what? Say mu naught I upon 2 pi r, B as a function of r. Here the B is inversely proportional to r, but r varies from capital R. So on surface at this point, what the magnetic field? You will write mu naught I upon 2 pi capital R in place of this small r. And in infinity, when the point P lies at infinity distance, so 1 upon infinity is equal to what? Say 0. So here, if you make the graph on the surface, what is the magnetic field? Say mu naught I upon 2 pi r, and it is decreasing. All right, it is decreasing. P is inversely proportional to r. Fine, copy this. So let's see the third application. You have to find B due to infinite solid current carrying conductor, right? Current carrying conductor. What is that? Suppose this is the solid cylinder or solid conductor, but it is infinite length, right? The radius of this is the axis, right? This is what? It is axis. This is capital R. Fine. This is the B, and R is equal to 0 to capital R, small r. The magnetic field you have to find, and the current I is distributed. Current I is distributed over the circumference. Is it clear or not? Fine. So again, you have to make the graph between B and variation of B with distance d, and the two cases will be there. The case 1, right inside. Inside mean the point P lies here. This is the point P at distance R. So you have to assume a current carrying, you have to assume an Amperian loop to find the magnetic field at this point. Is it clear or not, you tell? Right, this is the Amperian loop. So the value of R will lies from 0 to capital R inside. All right, and you will apply the Ampere's law. B dot dl is equal to what? Say mu naught into I enclosed. Listen, on this surface, the current is I. If you consider this small loop of small radius R, the current enclosed here will be what? Tell me. It is I dash. Then I dash will be less than this I. You understand or not? This I dash will be less than I. And how to find this I dash enclosed in this Amperian loop? Using unitary method. How? The current here is distributed over the area. So if you consider what is its area? On the pi r square area, the current distributed is over I. So on 1 meter square area, the current is I upon pi r square, or not, you tell? So what is its surface area? It is pi r small r square upon pi r square into pi r square. And this is nothing but I dash is equal to I upon r square small r square. And this is equal to the I enclosed in this case. You are getting or not, you tell? Yes. Now, if this is the I enclosed, I upon r square into small r square. If you consider the dl vector, and this is the b vector, so the b again come out, the theta is what? 0. So b dot dl is b dl cos 0, and b comes out from the integration of dl. Integration of dl mean, if this is the dl, the integration mean the 2 pi r, small 2 pi r mu naught I r square upon r square. If you further simplify this, 1 r will cancel out. B is equal to mu naught I small r upon, right, 2 pi capital R. Right. So this is the magnetic field inside as a function of small r. Right. You will see the B is directly proportional to R. All right. B is directly, and the R values varies from 0, mean on its axis. What is the magnetic field, you tell? If you put R is equal to 0, it is 0, the magnetic field is 0. And at R is equal to capital R on the surface here, right, mu naught I, put capital R is equal to 2 pi R. This is R square, this is R square. Here it is R square. So the answer is mu naught I upon 2 pi R. All right. If you want to draw the graph, at R is equal to 0, the magnetic field is 0. At R is equal to capital R, the magnetic field is, tell me, mu naught I upon 2 pi R. And it varies linearly. B is directly proportional to R, right? Copy this. So now we can discuss the case 2. What is the case 2? Say outside. What is the meaning of outside? The point is outside the wire. It means R is greater than R is less than infinity. Is it clear or not? So now we continue the outside. Outside mean the point P is outside the current carrying conductor, right? So here we have to find the magnetic field. So for finding the magnetic field at outside, we have to consider the Amperian loop, and this is the dl portion, and the magnetic field assumed to be B. Suppose this distance is R from the axis. All right. Now if you consider this is the Amperian loop, so in this Amperian loop, you tell me the all current is enclosed in this Amperian loop. If you apply the B dot dl is equal to mu naught into I enclosed. So what is the current enclosed in this Amperian loop? The all current is enclosed So this is equal to I. And B dot dl, the theta again is 0 degree, right? So it is B dl cos 0. Fine. Integration, it is mu naught I. If the B is common, the integration of dl, right, is equal to mu naught into I. What is the integration of dl? Is nothing but the circumference is equal to 2 pi r, right? Mu naught I, right? B is equal to mu naught I upon 2 pi r. Is it clear or not, you tell? So if you consider the outside, the magnetic field is mu naught I upon 2 pi r. Here B is inversely proportional to r. Are you getting or not? Fine. So the value of r varies from surface to infinity. So on surface, r is equal to capital R. What is the magnetic field value? Mu naught I upon 2 pi capital R, which is same as we have found in with the help of the internal magnetic field expression, and r tending to infinity, so it is 1 upon infinity becomes 0, and B is varying inversely proportional to r. So outside the magnetic field varies like this. Is it clear or not? And this is inversely proportional to r, right? Copy this. So read this question. In this question, a long state solid conductor and the radius of the solid conductor is 5 centimeter, right? Carries the current. Total current is what? Say 3 ampere, right? And it is uniformly distributed. You have to find the magnetic induction at r is equal to 4 centimeter, that is inside, from the axis of the cylinder, and the relative permeability is also given as the 1000, right? So here the internal inside the magnetic field you have to find, right? For the solid conductor we have the two formula, inside and outside. So the outside magnetic field is simple mu naught I upon, right, mu naught I upon 2 pi r, and inside the magnetic field is mu naught I r upon 2 pi r square. You will remember this. Are you getting or not? It is inside. So, but here the relative permeability is also given. This is given in the, for the free space. If the magnetic material is this, if some type of material whose relative permeability is mu r, so you have to multiply by mu r also. Is it clear? Right. So now we can put the value, the B at r is equal to 4 centimeter, right, inside. Mu r is 1000. Fine. What is the mu naught value? 4 pi into 10 to the power minus 7. The value of current, the total current is what? Say 3. What is small r? Small r is 4 centimeter, right? Divided by 2 pi into r square. R is what? Say 5 into 10 to the power minus 2 whole square. Is it clear or not? Now, if you simplify this, you will get the answer. It is 2, 10 to the power 3 and 10 to the power minus 7. It is, and 2, 3 2 ja 12, 3 4 ja 12, 24 upon 25. Right? This is 10 to the power minus 6 divided by minus 4. It is 24 upon 25 into 10 to the power minus 2. It is 24 upon 25 into 100 into 10 to the power minus 4 it is, right? 24 into 4 into 10 to the power minus 4, right? 4 chok 16 and 96 minus 4. 9.6 into 10 to the power minus 3 Tesla is the correct answer, right? Copy this. So read this question. In this question, a solid cylindrical wire and having the radius capital R. All right, this is the R. Current I, total current on the wire carried is I. Right, you have to find the ratio of the magnetic field from the axis at R by 2 distance. This is R by 2, right? And from the axis at 2R. Are you getting? So for inside, the inside magnetic formula, magnetic field formula is what? Mu naught I, right? Mu naught I R upon 2 pi r square. So at r is equal to r by 2, the B1 is mu naught I r by 2 upon 2 pi r square. It is equal to mu naught I upon 4 pi r. Is it clear or not, you tell? Yes. And outside magnetic field B2 is mu naught I upon 2 pi r, small r, and small r outside here it is 2r. So mu naught I upon 4 pi 2 pi into 2r. So it is equal to mu naught I upon 4 pi r. It means the magnetic fields are same. So B1 upon B2 is what? You tell. 1:1. Right. So the first option is the correct option. Look, if you consider the graph is like this. Is it clear or not, you tell? Right. So from the axis r is equal to r by 2. This is r by 2. And this distance is 2r. Right. This distance is 2r. Right. So if you look the graph, the same magnetic field which is equal to mu naught I upon 4 pi r is same, right, at distance r by 2 and 2r by 2. Are you getting? This is r by 2 and this is 2r distance. The magnetic field are same. It means there will be always 2 points from the axis of rotation. From the axis of rotation, 1 point inside and 1 point outside. The magnetic field is same, right? Keep this remember in this your mind, right? So read this question. In this question, solid cylindrical wire of radius r is given and it carries, right, the current I, right, uniformly. The radius of this wire is supposed to be capital R, right? A magnetic field is 5 microtesla from the axis, right? It is distance r. The magnetic field here is 5 microtesla. Are you getting? You have to find the magnetic field at a point r by 3 from the surface. From the surface, the point is at r by 3 distance. This is what? R by 3. So tell me, what is the distance from axis? Tell me. From axis, this distance is, yes, r minus r by 3. R minus r by 3. Right? So 2r by 3. So this supposed to be the point 2. So the B2 point will be found mu naught IR upon 2 pi r square formula. Right? And the outside at this point, suppose 1, the B1 is to be found mu naught I upon, say, 2 pi r, this formula. What is capital, what is small r over here? You tell. 2r. And the value is supposed to be 1. It is mu naught I upon 4 pi r. Is it clear or not, you tell? Yes. This is 4 pi r. Fine. Yes. Here, what is the value of r? We have to find mu naught I. This is 2r by 3 divided by 2 pi r square. So 2 will cancel out. Also the r will cancel out. So this is 3 pi r. This is the B2. Are you getting or not, you tell? Yes. The B1 value is known. It is 5 microtesla. B2 is to be found. So how to do that? Listen, the simple way, divide them. Right? Divide them. B2 divided by B1. Fine. What is B2? It is mu naught I upon 3 pi r. What is B1? Mu naught I upon 4 pi r. So this is equal to 4 by 3. So B2 is equal to 4 by 3 into B1. 4 upon 3. What is the B1? 5 microtesla. This is 20 upon 3 into 10 to the power minus 6 Tesla, or 20 upon 3 microtesla is the magnetic field at this point, right? So the second option is the correct option, right? Copy this. So read this question. In this question, there is a hollow cylinder, right, and which carries the current I, having the inner radius and the outer radius is 2r. It means, suppose this is the cylinder, right, and the material is this, right? This side is air, also this side is air, right? And current is, total current is I, and it is passing like this. Is it clear or not, you tell? Right, it is hollow, right? The inner radius is what? Say r, and the outer radius is what? Say 2r. Is it clear or not? The total current is I, and we have to find the magnetic field at a point 3r by 2 from the axis. If this is the axis, you have to find the magnetic field at distance r is equal to 3r by 2. Is it clear or not? Right. So this is very good question. Right. This is the side view. If you see the top view, right? If you see the top view, from the top view, this is the inner circle or this is the outer circle. This radius is r and this radius is 2r. The current is distributed over this material like this, right? And it is coming out from the plane. Is it clear or not? You tell. Right. And you have to find the magnetic field, right? You have to find the magnetic field at distance 3r by 2 from this axis, right? Suppose this is the axis. Total current is I. You tell me, the current is distributed over the area, right? So if you want to find the magnetic field at this point, you will assume, right? You will assume an Amperian loop like this. The Amperian loop is like this. This is the Amperian loop, right? Right. And if you choose, the magnetic field will be the circular like this, right? If you choose, this is the element dl and this is the magnetic field B. So you can apply the Gauss's law. You can apply the Ampere's law. B dot dl is equal to what? Say mu naught into I enclosed, right? You tell. If total current is this and total I, if you consider this is the portion only, right? This is the portion from r is equal to r is equal to r to r is equal to 3r by 2. So this is the portion where the current assumed to be the I dash, right? Although from r is equal to capital R to r is equal to 2r, the current is what? I, right? But we have to find the current up to 3r by 2, right? Up to 3r by 2. So how to find the current, please tell? Right, using the unitary method, right? What is the total area? This annular ring, you can assume what is the area of this ring is pi 2r square minus pi r square. So this is equal to 4 pi r square minus pi r square, right? It is equal to 3 pi r square, right? So in this 3 pi r square area, what is the current? You will say I, right? For 1 meter square, what is the current? Say I upon 3 pi r square. All right. So in which area now the current I dash to be found? From radius r to 3r by 2. So what is this area? This area. How to find this area? This area is from r to 3r by 2. So the outer circle is area is pi 3r by 2 whole square minus inner is pi r square. Is it clear or not? So this is equal to how much? It is 9 pi r square by 4 minus pi r square. So it is equal to what? Say 5 pi r square by 4, right? So this current I dash is distributed only in this strip, and the area of this strip comes to be 5 pi r square, right? So in 3 pi r square, the current is I. In 1 meter square, the current is this. So in 5 pi r square by 4, the current is I upon 3 pi r square into by 4, right? So this current is 5I by 12 and this is equal to I dash. Is it clear or not, you tell? Yes. Fine. So this is the I dash and this is the I enclosed here, right? So now you can think this is the B dot dl, is equal to mu naught into, what is the current enclosed? It is 5I by 12. This is 5I by 12. Is it clear or not? If you assume this is the length dl, this is the length dl, the magnetic field is B, suppose. So the angle is what? 0 degree. So B dot dl is what? B dl cos 0 mu naught 5I by 12. All right. The B comes out from the integration, mu naught 5I by 12. B is equal to what? Say 2 pi r. The integration of this dl, this dl is what? This is the circumference, right? And what is this circumference? Say 2 pi r. And what is the r? Say 3r by, yes, 3 by 2r. 2 will cancel out. So this circumference is 3 pi r, right? So it mean all this length, all this circumference is equal to what? Integration of dl is equal to 3 pi r is equal to mu naught 5 by 12. B is equal to what? Mu naught upon 36 pi 5I. B is equal to mu naught, right, up 5I, 5 mu naught I upon 36 pi. So this is the answer, right? Copy this. Oh, R is left. Wait for 1 minute. This R is left, right? Yes. This R is left. So you can copy now. So read this question. In this question, a long straight and solid wire, and it is the solid wire, right? And it is infinite wire, no doubt. And what is the radius? Its radius is 2 millimeter, right? And what is given? It is current is distributed uniformly over the cross section perpendicular to the axis of the wire, right? Perpendicular to the axis of the wire, right? Long uniform over its circular cross section, magnetic field at distance 2 millimeter. Here the magnetic field is given as B. Fine. It means on the surface is you assume to be R. Are you getting or not? At a distance 1 millimeter, right? Here on the surface, what is the formula? For the surface, magnetic field is mu naught I, suppose this is the current, 2 pi r. And the r value is 2 millimeter, we can put it later, right? Now, they are asking the magnetic field at 1 millimeter, right? From axis, this is the axis, the radius, this distance is r, and r is equal to 1 millimeter inside. What is the magnetic field formula you tell? Mu naught I r upon 2 pi r square. Is it clear or not you tell? This is the equation number 1, equation number 2. So 2 divided by 1, that is B dash divided by B, right? So what is the B dash? Mu naught I r upon 2 pi r square divided by mu naught I upon 2 pi r. Fine. So it is equal to what? When you will simplify, everything cancel out, r upon r will left. So B dash upon B. So B dash is equal to r upon r into B. What is r? Put 1 millimeter only, right? And capital R is 2 millimeter. So unit will cancel out, and this is the B. So answer is B by 2, right? The fourth option is the correct option. Copy this. So read this question. In this illustration, long straight wire, right? It is a solid wire, right? And the radius is 3 millimeter, right? This is 3 millimeter, and the current density is given. The current density is nothing but J in ampere per meter square, 100 ampere per meter square. That is in 1 meter square. What is the current? Say 100 ampere. In 1 meter square, the current is 100 ampere. The magnitude of the magnetic field at the A part, 2 millimeter. 2 millimeter is the inside. Fine. This is the B1. So for the B1, what's the formula you will apply? Mu naught I r upon 2 pi r square, right? But here the current is nothing but J. is, suppose the total current is I and the radius is R. So it is I upon pi R square. I upon pi R square it is given. Right. So you may write mu naught R upon 2 pi into I upon, sorry, it is I upon pi R square. Can you write this formula like this? I upon pi R square. So what is the value of mu naught? 4 pi into 10 to the power minus 7 upon 2. Right. What is small r? Say 2 millimeter. Right. What is value of I upon pi R square? I upon pi R square value is 100. Is it clear or not, you tell? Right. If you put the value, 2 will cancel out, 4 pi into, right, into 10 raised to a minus 8. Right. 4 pi into 10 to the power minus 8 Tesla. So this is the magnetic field inside. All right. And in the B part, they are asking the magnetic field 4 millimeter. Right. This is 4 millimeter at B2. Right. So in the B part, the formula you will apply mu naught I upon, right, 2 pi r. Right. 2 pi small r. Mu naught I upon 2 pi small r. R will be 4 millimeter. But the value of I, listen, from here 100 is equal to I upon pi r square. So the value of I is equal to 100 pi into r square. And the r will be here 3 millimeter. Right. So the value of mu naught, the mu naught value I am putting, it is 4 pi into 10 to the power minus 7 upon 2 pi. What is the value of small r? Outside 4 millimeter r. And what is the value of I? It is 100 pi into r square. What is the capital R? It is 3 millimeter, right, whole square. Right. Now it will cancel out, 2 into 10 to the power minus 7. This is pi upon 4. Pi upon 4 into 100 into 9 into 10 to the power minus 6. So this is 9 pi and 2 to the 4, 9 pi by 2 into 10 to the power minus 7 into 10 to the power 2 into 10 to the power minus 6. So 9 pi by 2 into 10 to the power, how much it is? 10 to the power minus 6 pi, ये भी तो रह गया, this into 10 to the power minus 3 is left, right? So when it goes in denominator, numerator it may minus 3, so it become minus 8. So the B2 is equal to 9 pi by 2 into 10 to the power minus 8 Tesla. Fine. So the B2 is this. So option third is matching. Is it clear or not, you tell? Copy this.